Okay. Hi, everyone. I'm Chenyang from Northeastern University. And today I'm going to share our work, hierarchical synthesizing near-optimal collective communication schedules for heterogeneous GPU clusters. Let's start from the big picture. Collective communication is the backbone of large-scale machine learning. Over the past few years, model sizes have exploded. Parameters keep increasing. A model may experience multiple stages, such as pre-training, fine-tuning, and online inference. Each stage needs different communications. Under the hood, there are GPUs, NICs, switches, and different network architectures. In the middle sits the communication library. It bridges the raw hardware and engines and the models. Here's the catch. Collective performance depends a lot on the schedule. Take a Nichols ring schedule as an example. Here are two servers, each with 8 GPUs. Inside the server, they connect by NV switch. Across servers, they use NICs. Nichols links all 16 GPUs into a long ring. Each data chunk starts at one GPU and goes hop by hop until everyone has it. For large messages, we want full bandwidth. But in the ring, for every 7 inter-server hops, there's only 1 inter-server hop. This means Nichols always use a fixed bandwidth ratio of 7:1 between inter-server and inter-server. However, a real GPU cluster may be different. On the H800 cluster, NVLink bandwidth is about 4 times the NIC bandwidth. So this ring schedule with network bandwidth. In practice, we just replace 1 inter-server hop with one inter-server hop. This can improve performance. For small messages, latency dominates. Rings are bad here because data must go through many dependent hops. A better idea is to send to multiple GPUs at the same time. So the problem is clear. Fixed schedules can be suboptimal because they waste bandwidth and add latency. So what about handcrafting better schedules? Well, it's basically impossible because there are so many factors to be considered. First, the topologies are very different. There are different GPUs with different inter-host and inter-host connections. Second, there are different collective primitives, each with different communication patterns or demands. And third, datasets ranges from tiny kilobytes to gigabytes. Put all that together, manual optimization just doesn't scale. Then let's try automation. Just generate schedules automatically. Sounds nice, but the search space is too large. First, there are many routing paths between 2 GPUs. In this example, sending from GPU 0 to GPU 5 has 2 choices. Go intro first, then inter, or inter first, then intro. Second, one chunk can be sliced into multiple pieces, and each piece can take a different path. Third, when 2 chunks go through the same link, either one may go first. That's another branch. Moreover, as large language models scale, maintaining perfectly homogeneous clusters is becoming increasingly difficult. Heterogeneity is simply the new norm. This is driven by a few practical realities. Data centers expand incrementally through different purchase batches. Organizations want to prevent vendor lock-in, and we frequently see heterogeneous hardware mixed together. Even within the same hardware generation, the intra-node topology can vary widely. As you can see in the table, mixing NVLink and different NIC speeds creates a highly irregular network. This message variance directly breaks the existing solutions. When confronted with a heterogeneous cluster, their automated synthesize either fails or take an intractable amount of time to find an optimal schedule. So Why do existing synthesizers fail here? Because they rely on a mathematical shortcut, topology symmetry. As illustrated here, they decompose the network into identical isolated dimensions, such as uniform internode link domains and symmetry internode switches. Because these groups are perfectly identical, the solver only needs to compute an optimal scheduler for one localized group and then simply replicate it across the entire cluster. However, in a heterogeneous cluster, this perfect symmetry completely shatters. When we introduce incremental upgrades, mixing different GPU generations or dealing with diverse link bandwidths, these uniform dimensions cease to exist. You simply cannot copy-paste a schedule from an H20 node onto an A100 node, nor can you mirror schedules across asymmetric network tiers. Furthermore, another root cause lies in their mathematical modeling. As shown at the top, existing work either model the aggregation computation time of a transfer or they slice time into rigid intervals. But in a heterogeneous cluster, link capacity vary widely. A chunk transmitted over Rocky takes much longer than 1 over NVLink. Because these synthesizers don't constrain the macro execution order of these primitives, we end up with the scenario on the bottom left. A long tail primitive blocks the execution pipeline, forcing faster independent operations to solve. This creates massive pipeline bubbles and destroys the theoretical bandwidth. If we try to fix this within existing frameworks by using fine-grained epochs to capture these variations, the solver's search space explodes. As shown on the right, this creates a sharp trade-off. Synthesize time spikes beyond 14 hours for just 32 GPUs, making it intractable for production scales. To overcome the limitations of continuous time models, we built HeteCCL around 3 core designs. First, we formulate the collective scheduling as an SMT model, a problem. Second, we introduce the chunking abstraction by quantifying link capacity capabilities into discrete parallel subpaths. We force primitive durations to align the step level. Finally, to handle the massive search space of heterogeneous cluster, we drive our SMT solver using counterexample-guided inductive synthesize. Now let's look at how we model schedule synthesize as an SMT problem. The key idea is straightforward. We represent all states and events as variables and encode everything into constraints. At the beginning, each GPU holds chunks. Our goal is for every GPU to receive all chunks. This is a classic all-gather example. First, we encode the network topology into constraints. This includes the logical capacity between any pair of GPUs. Second, we encode the schedule itself as a constraint. It formalizes at step S, send chunk C over link L. We solve all these constraints with an SMT solver. Our target is to minimize the total number of steps, but this approach has a critical bottleneck. As the system scales, we face a search space explosion. This is where our chunking model and CGS helps. Let's start by unpacking the first of these mechanisms, the chunking abstraction. How do we eliminate those pipeline bubbles caused by uneven execution times? Instead of resting with continuous time modeling, we enforce step-level capacity abstraction. As you can see in the diagram, we normalize the transmission process into uniform time steps. Based on the physical bandwidth, we assign each link the discrete logical capacity. This capacity strictly dedicates how many uniform chunks a link can transmit in parallel within a single step. We transform a highly intractable continuous time routing problem into a discrete packing problem. The synthesized algorithm is no longer guessing start and end times. It is essentially searching for a near-optimal packing tree that maximizing parallel chunk overlap. When mapped to our SMT solver, these logical capacities become simple, rigid binding constraints per step. And our optimization objective is simply to minimize total algorithm step. Now that we face our next major challenge, scalability. To break this bottleneck, HeteCCL leverage counterexample-guided inductive synthesis instead of forcing the solver to process all global constraints at once. We use an iterative loop. We start with a fast, greedy candidate schedule. Naturally, this might violate physical link limits. During our verification phase, we don't just throw out the bad schedule. We identify the exact earliest time step where a violation occurs. We call this checkpoint. By locking the valid history before the checkpoint and converting the counterexample into new SMT constraints, we prove factorial magnitudes of invalid search branches. We evaluate HeteCCL on real clusters, including with 100 testbed with a closed fabric and H20 cluster with multi-rail networking. We constructed highly asymmetric testbeds. Instead of standard uniform setups, we mixed different node configurations with the cluster. For example, bridging 4 GPU servers with 8 GPU servers. And varied their NIC interconnection patterns. We test all gather and all reduce and comparing against Nico, Taco, and Tico. For gather, our synthesized schedules achieved up to 2.5 times speed up Nico and 4.4 times improvement over Taco. For reduce, the trend holds. For large data size, the improvements are smaller but still clear. For the synthesis time, HeteCCL is up to 2 orders of magnitude faster than Tico. Let me wrap up. Collective communication is critical for large-scale machine learning. Fixed schedules are suboptimal and the current synthesizers don't scale. Our solution, HeteCCL, combines chunking modeling with counterexample-based pruning. We see significant synthesis speeds up and performance improvements. Thank you. I'm happy to take questions.